So now let's take a look at the topic of variance. We have actually introduced variance for samples, and now we want to generalize it for distributions. And perhaps you remember how we did that for the samples. We looked at the difference between the sample means, squared it, and divided by n-1, essentially considering the mean squared deviation. And we need to do something similar now for random variables, except that instead of the arithmetic mean, we will consider the expected value. And exactly what we are doing is we look at x squared and determine its expected value. So simple, so good. And that is the variance. And if we write it out, let's do that now. It essentially means that for each value psi, so psi minus is the expected value of x, so psi squared times pi, which means our values are now not psi anymore, but they are psi squared. And then we simply take the expected value of these values, and that essentially corresponds to the second moment that we did for samples. Namely, we also want that. So now we have defined the mean squared deviation as the expected value of the distance from xi to m. Exactly. That is one formula, and the other formula does again what we already know, namely the second moment. The pi is thus replaced with a density, and the sum is replaced by the integral for continuous distribution. We often write sigma squared for the variance, or simply write var of x. Exactly. Well, that is now the formula, and I would say let's calculate a direct example. And of course, we will make it as simple as possible. Namely, we take dice, roll once, and want to calculate the variance. And for that, let's quickly think again. What was the formula? Well, what we need to do is we need to multiply xi squared by pi and write what was that again. So we already know that is 3.5 or 72, and the xi's go from 1 to 6. That means if we do that, then when xi equals 1, we have 1 times 3.5, which is 2.5, squared times 1/6. When xi equals 2, we have 1.5 times 1/6, and so on. Yes? 0.5 squared times 1/6. Then for xi equals 4, we have plus 0.5 squared times 1/6, plus 1.5 squared times 1/6, plus 2.5 squared times 1/6. Alright, then let's calculate that briefly, but we do this by quickly considering what is the minus. We can forget. Minus squared is 2001, recently out. Then let's quickly calculate 2.5 squared, which is 5/2 squared. So 25/4. Let's write that down, 25/4. I can already do 6 here. Plus, then we look at 1.5, which is 3/2 squared. So 9/4, so we have 9 over. 4 times 6. Then we have 0.5 squared, which is 1 to 4. So 1 over 4 times 6. And we have all of that again, which means we have 2 times 2. Okay, that means we get 24 in the denominator. And now let's quickly add everything together. 50, 1802. And that results in 70, 24, or 5 and 30, 12. Okay, yes, not a nice value, you can't say that, but yes, that is the variance of a dice roll, really calculated by hand. Exactly. Yes, that was the example, calculated by hand. And so we continue and want to understand whether there are calculation rules that help us determine the values overall. And indeed, one of the most important formulas is the so-called shift formula for the expected value. Let's take a quick look at it. So we have a random variable x, an expected value, and a variance sigma. And we see that sigma squared, that our variance is nothing other than how we can describe the variance as we take the expected value of x and subtract. I need to think briefly about what that means. So this is e of x squared. Okay, and that is not the same, because we have learned that, if you still remember, e of x times y is e times x times e of y, but only if x and y are independent. X is not independent of itself, which means e of x is not equal to e of x squared. And this statement says that the difference between these two is exactly the variance. And you can actually see that quite well. I want to explain it to you briefly. You remember that the variance is nothing other than the expected value. So of this term here, and we can expand that. Let's do that. So it's e of x squared plus square. And now we can use the formulas for the sums and differences of expected values, which then say that it's e of x squared plus e to the power of minus 2 times x plus e of, okay, that was just the part. We write down the first term, e of x again. And now you can use that. You can also factor out a factor from the expected value. That means we can write minus 2 times is just a constant times e. And now we have to consider what e of is just a constant, whether the expected value of a constant is this constant, which means it simply comes out here. And if we now see that e is nothing other than, then it stands here. Minus 2. And we stay at x minus 2021. And that is exactly what the formula says. And that is a very nice statement. It can help us calculate the variance a bit faster by first calculating the expected value. And then you can also calculate the expected value of x for the dice roll, and you will arrive at the same result. This is the very important shift formula. Yes, now we want to address the following question. Namely, we have the following random experiment. We have a die, and we want to look at the tenfold sum of the faces as the random variable. This means that the corresponding probability distribution looks as follows. So you can have a 10, you can have a 20, a 30, a 40, a 50, a 60. So these are our C's and our P's remain. 1/6 each. Exactly. And it is very important to distinguish this from the random experiment where you have 10 dice and roll them to form the sum. We have seen that the expected value will be the same, namely 10 times the expected value of the die. However, for the variance, it is a very significant difference. Exactly, these are simply different values that result for the variance. Yes, and what effect do you see? Well, on the one hand, our expected value becomes 30, which increases by a factor of 10, as we have already seen. And what we have overall is that the she allows us to pull out a 10 from the she, because she is 10 greater. We pull out the 10 and everything becomes 100 times greater. So you can expect that it will be 100 times the variance of a die. And exactly that is also the following. If x is a random variable and we have two real numbers a and b, and we have a new random variable y, x plus b, then the variance of y is equal to a times the variance of x. That means we can pull out the a as a square, as we just saw in the example where we had the factor of 10. By the way, we had no b. Yes, we only said the tenfold die roll. But we could also have said that we take the random variable of a tenfold dice roll plus the constant 3. And it is important to mention that the constant does not play a role, so the variance does not change when we add a constant. And it also makes sense because it essentially means that we are simply shifting the distribution to the right, and yes, thus, the spread does not change, but only the mean is shifted a bit higher. And for the standard deviation, it holds that there is no longer a quadratic relationship, but only a linear relationship. So that means the standard deviation will then be increased by a factor of 10. The standard deviation, by the way, is the square root of the variance. Well, that was the formula for when we have a factor and a constant. And essentially, the following question remains open for us, namely, what about the variance of x plus the variance of y? There are various possibilities. It could be the variance of x plus the variance of y. It could be squared. It could... Yes, the question is unanswered and we want to answer it in the next video. Take care.